Good morning and welcome to CMG's webinar series. The title of today's webinar is Sense and Respond, Why Not Predict and Prevent? Presented by SDS and ConicIT. The speakers today are Jacob Ukelson of ConicIT. Jacob has a proven track record in discovering and developing innovative solutions and has fostered innovation in many different environments, including both research and business settings. He is a senior advisor and director at ConicIT. Previously, he served as the Chief Technology Officer and Business Development Executive at IBM's Global Technology Unit and served as a Department General Manager at the IBM Thomas J. Watson Research Lab in New York. And first up will be Brian Lampe of SDS. Brian is the Marketing and Advertising Coordinator for SDS. He brings a modern yet straightforward approach to marketing within the mainframe community. He is experienced in pay-per-click, social media, and email-based campaigns. He works to extend the 34 years of trust in the SDS name. If you have any questions during the presentation, please type them into the chat box and we will answer them at the end. With that, Brian?
Thank you, Steve. Hello, everyone. Thank you for attending our webinar today on ConicIT, Sense and Respond. Why not predict and prevent? My name is Brian Lampe, and I'm the Marketing and Advertising Coordinator at Software Diversified Services. We'll have a Q&A session at the end of this presentation. If you have questions during the webinar, please send them to us in your question box. You can also email them to us at info@sdsusa.com after this presentation. Here's our agenda. I will give you a brief introduction to SDS, Software Diversified Services. Then, Jacob Ukelson will be presenting ConicIT, Predict and Prevent. Following Jacob, we will have our Q&A session. Deb Hodson, our Sales Manager at SDS, is also on the line with us today. She'll be joining us for the Q&A session. Deb has 30-plus years in the IT business, with having been at IBM, HP, Candle, and now SDS, all in sales and consulting roles. SDS, or Software Diversified Services, has been providing mainframe solutions to the market for over 34 years. We have over 1,000 licensed customers worldwide, including Global 500 companies. Our headquarters are located in Minneapolis, Minnesota. SDS now supports over 20 ZOS, MVS, VSE, and VM mainframe systems products. Our flagship products are dedicated to network management, security solutions, and performance solutions. SDS is a leading provider of enterprise infrastructure software for multiple platforms with a 34-year history of developing award-winning support and customer-centric IT infrastructure solutions. Over the years, we've developed more solutions for the distributed environment, we've added to our mainframe portfolio, and we've partnered with key subject matter experts for excellent software solutions. Our development staff is continually providing rich, robust updates and enhancements to our products. SDS has strived to bring software solutions to the marketplace that provide both cost savings while still using elegant and state-of-the-art functionality. We would like to mention that the 42nd Computer Measurement Group CMG conference will be November 7th through the 10th. I hope you can make it to the International Performance and Capacity Conference this year in La Jolla, California at the Hyatt Regency. Start planning now. You won't want to miss a minute of this conference. Okay, I will now hand the webinar over to Jacob. Jacob?
I'm going to show my screen right now. Hi, everybody. Okay, there, now you should see the screen. Thanks for joining, and I'm going to be talking, as was mentioned previously, about this idea around, everybody is talking about sense respond, being able to react to things that happen in the business environment with respect to technology. And we believe that there's an opportunity now to look at sort of more advanced technologies that can use predictive analytics and try to catch the problems before users call in telling you that there actually is a problem. And that's the main idea behind this. What are the technologies that you need to employ to actually make that happen? So just some background first is that if we look at the mainframe, the world around the mainframe is changing, and so is the world of the mainframe itself. all these new workloads from mobile, web, and so on. In the end, for many large organizations, they go back and create transactions on the mainframe. And so these transactions actually act a bit differently than, of course, batch programs, but also they have their own kind of transaction footprint, which is a bit different than things that happened earlier. There's a lot of change in the world, both in the mainframe and in the distributed computing world, around what are the methodologies needed to keep things running 24/7, provide the user experience that's expected for today's technologies, especially since customers' user experience are shaped not only by your industry, whatever that may be, but by what they're doing in Facebook and what they're doing in LinkedIn. And so they have this expectation of what should be done and what computers should be able to do. And if anyone's ever gone to a DevOps conference, which is sort of the last thing you would expect from a mainframe, actually, over the last couple of years, there's a enterprise DevOps conference where there's quite a bit of activity around mainframe and applying these new methodologies to mainframe operations and development. And finally, of course, there's this topic of retiring skills that everyone knows about, that a lot of the people that have really deep mainframe skills are at retirement age or getting to retirement age. And there is an influx of new people, but they don't yet have the skills or the deep expertise that's been garnished over decades by the more senior folks. And so there's this gap there between the experience of the more senior folks, which are coming to retirement age, and the younger folks, which are just getting up to speed. And so the idea is, in order to be able to handle all those different pressures, it would be great to create this notion of a system of intelligence. And I'll talk in a little bit about what this notion of a system of intelligence is. But to manage production assurance on the mainframe that would preserve your operational integrity, but still increasing delivery velocity in a shifting IT landscape. And that's important because as these new workloads are coming on, organizations in the mainframe need to be able to handle and change much more quickly than it was ever required before. And so being able to build up the system so that it is both robust, which everyone expects the mainframes to be, so that's sort of a given. You don't get any extra points for being robust on a mainframe anymore. But now people are expecting it not only to be robust as it was before, to also be much more agile and being able to increase the velocity of delivery. So what is this notion of production assurance? What we believe is that if you combine a few things together, and they all exist in one form or another in the marketplace, you can actually put these pieces together. And the idea is to create a technology that is always vigilant. In other words, it's collecting information and gathering and learning all the time. Now, everyone that has a mainframe has a monitor. There's the 4 big monitors, and sort of everybody has at least one, probably multiple ones, probably maybe even different ones for different subsystems. But those systems are available, but it's impossible to get people to watch and be vigilant all the time. And so you want to be able to have some kind of automation there that can actually watch what's going on and have some understanding to be able to differentiate between things that are important and should generate alerts and things that don't need to generate alerts. As I said, monitors are great, but they're not necessarily very discerning about when they generate alert or not. Many of them have thresholds, but these are relatively gross thresholds, and they're not very dynamic. They're not learning and changing based on the workload and the application workload that's appropriate for that production environment. And so the second point is, well, you really need dynamic learned thresholds. In other words, if you look at it at the level of the application, what you want to be able to understand and learn is have the system learn and understand what are the thresholds that are important for that environment. And it's not a single threshold, of course, but it's dynamic. It's something that's changing all the time. It would be great to essentially have a threshold for every second of every minute of every hour of every day of the year, and have it learned from what is actually going on in production and have it tailored to your specific production environment. Use that information, use that as I'll call it, behavioral analysis, this understanding of the behavior of your production system, and apply predictive analytics to it. And I'll talk about what that entails. And then use that to create accurate, actionable alerts that happen before your users are calling in. So in other words, it's there, it's watching, it's learned your system, and is continuing learning your system as time goes on. It's predicting, and I'll talk about what I mean when I say predicting. It's predicting problems and then providing accurate actionable alerts based on what it's seeing. So the first question is, how can you do this magic called predictive analytics, right? And so if anyone has ever used any of the statistical tools out there like SAS or SPSS or other tools, everyone knows that there's all kinds of different algorithms that you can choose sort of automatically, and they'll do some level of predictive analytics. The problem is that in order to be able to do this right, you have to have a model of the system that you're trying to predict it for. So in other words, if you just try to use generic prediction without any understanding of what's going underneath, the prediction probably won't work very well. You know, the example I tend to give people is that if I could predict anything, then of course I would apply our system to, not to the mainframe necessarily, I'd apply it to the stock market. And that would be a lot more lucrative. But the problem is the system that understands the mainframe does not understand the stock market, and it's not clear if there's any predictive model that would understand the stock market. So you have to create your models in such a way that they understand what the domain that you're trying to predict, and that's the only chance you have of making something that works well. So the idea of being able to use general purpose statistical probability analysis in order to do prediction is great, and it will certainly be usable at any time. In other words, you can just apply it to anything, but on the other hand, it won't be correct and it won't be accurate, because the level of the model and the accuracy of the model is what makes sure that you actually get predictions that have meaning and that are useful. So what you really need is this notion of being able to do general purpose mathematical modeling. So you have to have, of course, very powerful statistical models in order to be able to do this, but you have to be able to understand the domain. So your model has to incorporate within it understanding of the domain that you're trying to address it to. And in this case, it's, you know, the mainframe, and it's how applications work in the mainframe. And then you can just give examples, right? And these are just really trivial examples, but it will hopefully give an inkling of what I mean by saying understanding your basic context, right? CPU usage must always be positive, so that's kind of simple. Locked resources have a big impact on your performance. Mainframes, queues are very important. You need to pay attention very closely to the way queues are building and releasing themselves. And this is not generic. In other words, what you need to be able to do is something that you can't apply to anyone, but you can do a kind of separation of concerns. You can use general purpose statistical, or pick out the appropriate general purpose statistical models, and then apply on top of that the specific model to the mainframe. And that way you get the best of both worlds. You have some general purpose models that are very powerful, but on top of those general purpose models, they then apply the specific domain expertise to make sure that they work in the environment of the mainframe. So understanding the domain context means you really need to understand what are the variables or what are the things that you need to pay attention to. Now, any given monitor on the mainframe has hundreds or thousands of parameters that you could be looking into. And if you think about being able to aggregate those together in order to get information, then you have a multiplier effect, right? You have actually many more things that you could be looking at. And so when I mean domain context, the important things to be able to understand what exactly are the parameters that you need to be paying attention to, what's more important, what's critical, and what's not. And so if you think about what is the notion of an anomaly based on the parameters, so you could think of anomalies around time-based related parameters. So in other words, one of the things that is actually very powerful to do in a production system is to pay attention to the time aspects of the various parameters. In other words, being able to analyze it down to the second of a minute of a day and the cyclical pattern of a week and the cyclical pattern of a month and special days. And so being able to understand what's going on in a holistic fashion around time is very, very important in being able to model and understand what's going on in a mainframe. And then, of course, there's this notion, because mainframes are what they are, work-related parameters, and I won't talk much about that, but in other words, certain units of work get done in a certain unit of time. And so, especially for a batch, when there's a batch window, right? There's certain things that take a certain amount of time, and if there's more time, they'll utilize less. If there's less time, then they'll utilize more. But essentially, the idea is that there's a certain amount of work that needs to get done, and depending on that amount of work and the period of time available to it, it will actually act a little bit differently. So those are things that you can be looking at and parameters that can be collected in order to be able to apply and understand in the mainframe domain this notion of predictive analytics. And then once you're able to do that, essentially what you've created is this notion of dynamic thresholds. Essentially, you're saying I'm learning and I'm understanding what is my expectation from a certain set of parameter or set of parameters at any given time, and then I can use that to create essentially what's equivalent to a very, very large number of dynamic thresholds for a specific parameter in a given context. And this notion of dynamic threshold is very powerful because then you can use that to have the system do higher level analysis and then use that in order to make decisions. And the decisions could be, for example, do nothing, right? The system can say, okay, I've looked at this, I see an anomaly. It's not as I expected, but I know this kind of anomaly is not really important for this specific kind of system. And therefore, I'm just not going to do anything about it. I'll just make myself a little note on the side. I'll log it. I won't really do much. Another thing it could decide to do, it could say, well, I need now to collect more information. What that means is that I'm seeing an anomaly. Things are not working as I expect. Then what I better do is start collecting a little bit more information, perhaps from other subsystems, perhaps doing it more frequently. And the idea is to be able to collect that and add that so that I can actually make a better decision down the road. So I can collect the information for the analysis and then use that extra information to make a better decision. And then, of course, the most the thing I can do is that actually has the most disruption associated with it is to provide an alert, right? You don't want to alert, of course, to things that aren't really alert worthy, I'll call it. So you don't want to alert every time you can. You want to alert only for things that are very important, but of course you don't want to miss anything. So you want to make sure that you have a built-in alerting threshold that says, I understand that this is important enough that I should deliver an alert, but I'm not going to deliver an alert for everything that I see. So this is sort of a guessing game. If I look at this, and this gets back to the idea of context, when I see a graph like this or when a machine sees a graph like this, it's kind of interesting, kind of sort of has a repeating pattern. But if I don't understand the context, I really can't understand very much about what's important here and what's not important here. But once I get the context, then all of a sudden it kind of becomes clear about what I'm seeing here. I'm seeing a week's worth of activity. The week seems to be cyclical. There seems to be a lot of activity going on at the beginning of the week, towards the beginning of the week, and less so towards the end of the week. So once I have the context, in other words, I have the model and the system understands what's going on, then all of a sudden it can start making predictions about what it's seeing, for example, on the week after. In the week after, in a production environments, except for special days and other kinds of unique dates and times, tends to be relatively cyclical. So I could be expecting to see something very similar the week after. Again, given the caveat that I understand the context, I'm continually learning, and as it's changing, I'm shifting my learning over time. But I can actually, once I have the context, be a lot more cognizant and much better and more accurate with my predictions of what should be. So here's an example of being able to use a prediction or showing what a prediction actually means. So if I look at this graph over here on the right, what I'm actually seeing is this green highway. The green highway is the predictive or behavioral analysis of what is expected of this specific parameter. It doesn't really matter which parameter it is or which combination of parameters, because it doesn't necessarily need to be only a single parameter, but an understanding of how I expect this to react. Now, what we're seeing from this point to the left, we're seeing actual data, and that's the line here. This is actual measurements. And what we're seeing from this point to the right is a prediction. This is what the system's assuming that this parameter should be doing in the future. So if we look at this of what's going on in the past, I can see that it's sort of bouncing around a bit, which is why you have both a higher and an upper and a lower boundary, but it's staying within the assumed boundary. And I think here's an important thing to pay attention to is that a lot of people, when they think about thresholds, they think about going over the threshold and overage. So for example, is it using too much CPU? And that's very important. Of course, trying to understand what too much CPU actually means is not trivial unless you have the content. For example, if you're using 85% CPU, is that good? Is that bad? Of course, the number itself is meaningless unless you understand the context of where 85% is relative to your specific production environment. But of course, if I know that production environment should be, given its context, at around 80% and it's 85%, well, then everything's probably just about fine. But what about lower bounds? Lower bounds are just as important. For example, if my CPU is at 20%, is that good or is that bad? Now, for many people that set thresholds, they'll just say 20%. Well, that's fine. It's way below whatever threshold they set. Everything should be okay. But that's not necessarily true. The reason is that it could be low if I don't understand the context. It could be low because it's being starved, right? So upstream, something's not giving enough work to the CPU, and therefore it's not just getting enough done. It's not that everything's fine. It's just that for some reason the problem isn't here. The problem's happening upstream. And so being able to, again, understand the context, and given that if I expect 50%, 70%, or 80%, and I'm seeing 20%, that's just as worrisome, if not more so, than seeing 85% when I expect 70%. So this notion of being able to understand the upper bounds and the lower bounds and understanding the context is very important. So in a nutshell, what I need to be able to do in order to be able to do this, I have to be able to build a detailed behavioral profile. So in other words, I have to have a learning system that looks at the production environment, watches it, and builds up a behavioral profile of how things should work. I have to have an internal model that's appropriate for the domain that I'm trying to understand. In this case, it happens to be the mainframe. I need to be able to predict based on that. And a prediction isn't a single number. The prediction is essentially a path. And the prediction is a set of upper and lower bounds that I expect on these parameters, not a single number. And of course, given that, I want to make sure that I have accurate alerts. And I need to have things that are generic. So in other words, this is working fine for most customers, but this time right here may be a special time for that given. So a customer needs to be able to tune it to themselves. So you want to have things that work out of the box and that you can just apply, but you also want to be able to fine-tune it to your production environment, right? Special days that happen only in your environment, or things that can be anomalies that you don't care about. So going back to this picture here, what I'm seeing is everything's fine. And right here, there is an anomaly, right? Outside the predicted bounds of the green highway. Well, is that good or is that bad? Or should I alert about it? It's certainly something I want to pay attention to, but I think the main question is, do I want to alert? Do I want to actually generate something that people need to pay attention to and tell them to look and come study it? Well, I'll get back to that in a second and talk about whether or not or when you want to be able to alert. But I want to talk about a little bit about why behavioral analysis is so important. And the reason is because mainframe systems are complex environments, very virtualized, running multiple workloads at the same time. And even if your application is debugged perfectly or your applications are debugged perfectly, that doesn't mean that you're not going to see glitches, problems, and anomalies in your production environment. And the reason is that the interaction between these different workloads and their usage of resources, they could be what's causing the anomalies and the problems. So even if every given application works perfectly, well, no, that's not true, but let's even assume that every single application works perfectly and it's been tested so that there's never any possibility of any bug, the interaction between them can't really be tested in a test environment. The unusual confluence of various kinds of usage patterns from lots and thousands, 100,000, 10,000s, or hundreds of thousands of users, of course, are going to cause very different usage patterns, where some of them may just cause problems. And there's no way to foresee that in any kind of testing environment. So what you want to be able to do is to be able to, in your production environment, to catch those, understand them, and fix them as quickly as possible. And so if I have a problem that happens over here in the left, right, that is where the anomaly occurs. Well, I want to be able to catch it as quickly as possible. But that's not usually what happens. What usually happens is that you catch your problems over here on the right, so much, much later. It could be that someone saw something and notified you, or in many cases it could be actually a user that calls up and says, hey, I've got a problem. It needs to be looked at. And so you're looking at it way after the original anomaly occurs. And the problem with that is that what happens over time is the actual remains or the data that you get from the actual problem goes away, and what you're seeing are symptoms. And I'll just give a simple example. For example, if there's a database lock that happened over here that all of a sudden starts to cause queues to accumulate, then, and the database lock is released over time, then all of a sudden what I'll see is that, there's nothing bad going on over there. But the queues have started to build, and way over here what I'll see is something that looks like a problem with my queues, overutilization of the CPU, not enough memory. I mean, there's lots of different things I could imagine that could be causing this problem, and because I don't actually see the things when the anomaly occurs, I can't really understand what's going. So if I could actually catch the anomaly, if I could see that when things went out of kilter, or very soon after that, it'll make it much, much easier for me to understand and solve the problem. And that's the main idea behind being able to use behavioral analysis to provide predictive analytics and find problems as early as possible. And I promise I talk about what this notion of predictive analytics really is. In some sense, predictive analytics is kind of a misnomer. It's not that we're predicting the future. What we're doing is we're saying this type of anomaly, that predicts the future, right? If I see this kind of that happening over here means that there's going to be users affected over there. And so from the user perspective, I've predicted the problem. But what I've really just been very careful in looking at anomalies and analyzing them, deciding what's important, and that's what I can use to understand and predict the fact that there's going to be a problem over here much later on. Well, even not much later on, just later on. So the idea behind an alert is that I'm seeing anomalies, and truth be it, you'll see quite a few anomalies, right? So there are things that go outside the boundaries for various reasons. And the idea is that you don't necessarily want to be to alert on everything out there, because if you do that, then you'll probably be providing too many alerts. What you want to be able to do is be smart about when things are anomalous, do you want to provide an alert? And in this case, there's two anomalies going on, right? There's this over here that happened, where it went outside its bounds, and then there's this one over here, where it went outside its bounds as well. Everything else seems to be just fine. So the question is, should I alert in both places? Do I alert in only one places, or do I ignore them both? Well, the answer is that I'm going to alert over here. And the reason is because for this specific parameter, so based on my context and understanding and the learning that I've done, I understand that it's essentially the integral underneath the time bounds, that it's outside of its boundaries. That's what is important, right? It's not a single spike that goes back, breaks through the boundary and then goes back. But I need something that's relatively long-lived. Again, we're not talking about very long, but essentially much longer than this. And the area underneath it is large enough, again, based on my understanding of this specific parameter and what I've learned about it, it's enough to generate alert. While this problem over here just doesn't have enough area underneath the alert, it tends to be very spiky. Therefore, based on my learning in the past, it's not something that I want to be able to, that I want to alert on. So this is the idea of being able to take the raw information, provide the predictive analytics, which is essentially the green highway. This is my prediction of what you'd be able to do. Look at the anomalies. This is what goes outside the boundary. Apply sophisticated analysis to that, and then decide when to alert. And of course, you want your alerts to be actionable. So it's not just that you're alerting saying, hey, there's a problem. You want to be able to get a lot more information about the problem as well. And so here's an example of an alert that's actionable because it's telling me how things sort of played out, right? If I can find the original anomaly and I can see what's going on, I can say, okay, look, I see other things happening, but if I want to scroll back in time and I go back to the earliest version. So it's really nice to sort of have a time machine and saying, let me see what was the first anomaly that generated, perhaps it was that generated all the other problems after that. I can look at it and very quickly say, aha, there's this problem over here, and that's what's causing, again, because of an understanding, and this is, again, just to be clear, this is not something that you would expect a system to do. To do the actual analysis, you want a person. So what the system can do is give you the information, point out the anomalies, point out the subsystems, and point out the sort of logic chain that was caused by that anomaly. That the system can collect for you. The actual fixing of the problem and understanding whether it's important or not and how you want to fix it, for that you need smart humans. So it's not that the expectation is that the system's going to go back and say, aha, I'm going to go fix your transaction for you. Not at all. What you can expect is for the system to be able to tell you pretty accurately where the problem is, and then have smart people understand what they need to do in order to fix the problem. Because sometimes the answer may be, you don't need to fix the problem. It was a one-time event. It's not something, perhaps there's just something wrong with one of your processes. It's not necessarily something that you need to handle. For example, I'll just give something that we saw with a specific customer. All of a sudden one morning they saw that they came back from the weekend and they saw that their system was not reacting properly and it wasn't processing transactions as expected. Now, this is a pretty big problem, right? And luckily it was sort of right after weekend, it wasn't a big peak period, but they were looking at it and they're saying, this doesn't make any sense. And what they went, they looked and they saw, well, essentially what was happening, this was caused by a lock on a database, right? They looked back in time, right, because it happened over the weekend. Because when they came in, they didn't see anything except the fact that transactions were going through the system slowly. They looked back in time and said, aha, there was this database lock over here, and the reason that happened is because we overran a batch window. Therefore, the transactions were not being processed as quickly as you would expect, and that's what caused the backlog to occur when business opened the first business day of that week. And so the answer in that case was essentially, well, there's not really anything we need to do for a system, right? We don't need to add memory. We don't need to add storage. There's nothing that we need to do from a system perspective. What we need to do is, make sure that all of our operators understand the procedures and make sure that that our system's not overrunning its batch window. If for some reason the automated system let it overrun its batch window. So, what's this idea of production assurance? So what I've been talking about till now is essentially this notion of how you can apply predictive behavioral analysis and predictive analytics in order to give you information about what's going on. But there's this notion that has, it's sort of peripheral to the mainframe. It's just something that's going on as a trend in the industry, is that everyone knows about system of engagement. They're, of course, changing. But, your mobile, your web, your 3270 screen, probably not, but essentially these are the systems that users use to actually access your systems and generate transactions. They address the systems of records. So, and these systems of records, in many cases, that's what's residing on your mainframe, right? So, and the world used to be this notion of systems of engagement. In other words, people being able to generate transactions, mobile, telephone, web, systems of record that kept the actual records, the business records, so that these transactions could be processed. And what seems to be arising now is this notion of a system of intelligence. In other words, being able to use data and being able to do predictive analytics so that you can provide smarts based on what you're seeing here. So it's great to have systems of engagement to talk to system of records. The other part of the triangle that seems to be really important and people are starting to talk about now is this notion of a system of intelligence, something that has and understands what's going on so that you can actually provide better service. Your system of agents can run better, your system of records will be better, and essentially you'll be able to provide better service to your customers. So if you want to talk about this notion of a full cycle performance system of intelligence, what would you need to be able to do? You want to be able to close the loop from your operations back to development so that they can go and essentially fix problems more quickly and hopefully prevent problems from happening. And this would a system that could provide that kind of information, in other words, a system that understands the operational aspects of production and is able to provide some level of analysis of issues, how they arise, and their root cause, that would decrease the need on deep mainframe expertise. Because otherwise, the way it's done today, and of course, systems run. I don't at all mean the systems aren't running and systems run well. But the reason systems run well is that there's a lot of human intervention there. And as I said earlier, a lot of these humans at the moment are retiring. And so the